Welcome back to the yet another lecture. So in the last video, we saw that we can actually have a one-down implementation for a given function. But another thing with multiplexers is that they can always be decomposed into smaller multiplexers, smaller order multiplexers, right? So this is yet another property which actually favors the use of multiplexers. So it's something like that higher order multiplexers can always be implemented using smaller order, lower order multiplexers. Fine. So it may be sometimes that you have a function which requires an 8 cross 1 multiplexer, but in your lab the 8 cross 1 multiplexer is not available. Right? What is available is say 4 cross 1 and 2 cross 1. So you can actually use a combination of these multiplexers and have the function implemented. Like here, the schematic I have drawn here, this one is a typical 8 cross 1 multiplexer. It has three selection lines, S2, S1, S0. And as usual, data inputs from I0 to I7. Now let's suppose I have a function which is a which has three variables. So our normal convention is that we connect the variables to the selection lines A, B, C. Then the data inputs, they are connected to either 0 or 1. Now since I am generalizing, I will take an example later on. So let's suppose this has input 0, 1, 2, 3, 4, 5, 6, and 7. So A, B, C are my variables, and 0 to 7, these are my inputs. Now I have to implement the same thing using a combination of two 4 cross 1 and one 2 cross 1 multiplexers. Fine. Now as far as the inputs go, they will be connected likewise. So this first 4 cross 1 multiplexer will have input 0, then 1, 2, 3. तो इसके चार inputs आ गए. Then 4, 5, 6, and 7 you will connect to the second 4 cross 1 multiplexer. Then their outputs will be connected to a 2 cross 1 multiplexer, and you will have the same function implemented here. But an important thing here is these selection lines. So यहाँ पे you have to be careful, and you actually start with the final multiplexer stage. So in this case, A will be connected here, the variable, and फिर जो आपके दो variables, the two variables that remain B and C will be connected here, these two selections in this order. Okay. Similarly, we can have another implementation where the same 8 cross 1 multiplexer here is actually being implemented in terms of 4 2 cross 1 multiplexers and a 1 4 cross 1 multiplexer. Again, the same thing, you will have your inputs directly applied here, input 0, 1 to the first 2 cross 1 multiplexer, then 2, 3 for the second one, 4, 5, third one, 6, 7. Right? So all of your inputs have been adjusted. And as far as what you call the selection variables go, in this case we started with A, so here it will be something like this: A, B. Then your least significant variable will appear here, one for each of these 2 cross 1 multiplexers. Right? So this is a very important property of multiplexers. You can actually implement a higher order multiplexer using a combination of lower order multiplexers. Now to put this into practice, let's take an example where I have a function. It's a function of three variables, and these are the minterms 1, 2, 3, 7 that are available, that are a part of this function. Right? Now straightforward implementation, you will require an 8 cross 1 multiplexers, wherein you will connect your variables directly to the selection lines A, B, C. Fine. Then for every minterm that exists in your function, you will connect to that to a supply, what we have been doing so far. So you have 1, so 1 will be connected, then you have 2, 2 will again be connected, then 3, 3 will be connected, and then 7 will be connected. Right? And the remaining, they will be directly connected, they will be actually grounded, so something like this. So I'm grounding 0, I am grounding 4, 5, 6, and this will implement your function f. Now let's suppose I don't have an 8 cross 1 multiplexer. I have to implement the same. This is again a straightforward implementation. Fine. So what I will have to do is Here are 4 cross 1 multiplexers. So I will first adjust my selection variable. So like I said, A will appear here, B and C will appear here. Then as far as the connections go, it will be something like this. So let me draw it here. Let's use the same color here. Yeah, let's use so that I are able to differentiate. So I will have a voltage line, then I will ground. So as you can see, 1, so this will be connected here, and then 2, 3, then this is 4, 5, 6, and 7. Fine. And then another line which is directly grounded, and we'll connect it here, 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 and here. Fine. Important thing here is you have to actually remember the order, the way you are connecting your variables. Right? So this is the straightforward implementation. I have used 8 cross 1 multiplexer. I can break the decompose the same into 4 cross 2, 4 cross 1, and 2 cross 1 multiplexers. Similarly, you can implement it using this. Fine. Then you can have another implementation which I taught last time, that you can actually go for a one down implementation, wherein I create a table. We'll quickly try to accommodate it here. I create a table just like this. So I have one variable complement form, normal form. Then I have to look for these inputs. So I will write all the minterms. Then I will encircle those minterms which are a part of the function. So 1, 2, 3, 7. Fine. So 1, 2, 3, 7. Then again I will work my way column by column. None of the columns are cells are encircled, so this corresponds to 0. This will correspond to A complement. This again will correspond to A complement. Here both the cells are encircled, so this corresponds to 1. So based on this, I will have the implementation using a 4 cross 1 multiplexer. So something like this. A 4 cross 1 multiplexer, I will have the required selection lines. It will have 2 selection lines. And then the data inputs I0, I1, I2, I3. So this is my 4 cross 1 multiplexer. Right? So this is a 4 cross 1. At the selection lines S1, S0, I will connect two of my variables B and C. Then on the input, yeah, now this is, let's save some time here. Now this is given I0, I1, I2, I3. So I will directly connect the inputs 0, then A complement, then 1, and this will implement my function. Then I can actually decompose this one. For example, in this case, I can implement this 4 cross 1 multiplexer using 3 2 cross 1 multiplexer, something like this. Let's have a 2 cross 1 multiplexer here, and then let me copy the same thing, another 2 cross 1 multiplexer, and copy the same thing here. Fine, just create some space. Just anyway, I think this is good. Okay, so these are my 2 cross 1 multiplexers. So what I can do is they will have one selection line. So let's get the selection lines here. Let me just drag it here. So selection line, selection line, selection line. Fine. Then they will have only two inputs, and the output of these two multiplexers, it will be connected to the third one, something like this. Fine. So first I will adjust the what you call the selection line. So in case may B will appear here, C and C here. Then I will accommodate these inputs in the order they exist. 0 A complement, then A complement, 1. So this will again implement my function. Yeah. Right. So this is again a very important property of multiplexers. You can always decompose a higher order multiplexer into a lower order multiplexer depending upon the availability. You may not have an 8 cross 1 multiplexer at your disposal. You can always break it down into a combination of 4 cross 1, 4 cross 1, and 2 cross 1 multiplexers. So the important thing here is, again, like I've been saying with, with respect to multiplexer, as far as logic implementation is concerned, it is actually the order of variables that matters, and you should know that for a particular implementation how I have to adjust to these variables. Like in this case, the most significant variable A will appear in the later stage of the multiplexer, like here, and the rest will be adjusted. Similarly, for these implementations, this is the way things work. So I'll stop here this video. Next video, I can take some examples. Thanks.